Hello everybody, welcome back once again to our next lesson. Today we're going to be jumping into a whole new topic, but it's very much related to what we've been studying with trigonometry. As we'll see as we move on here, we'll see how they're so tied in with each other. So today's topic is the complex plane. Our mindset message for today is that everyone's ideas are important, and we've used this before, but I specifically chose this because we're talking about imaginary numbers here, and if I jump into our prior knowledge, remember the imaginary unit I, and I stands for imaginary, is defined to be the square root of -1. And that also just means I is the number squared that gives me -1. You remember when we were younger, we previously didn't have any real number that worked to get a negative number when you square it, right? And the reason why I chose this mindset message is because mathematicians who first accepted the use of imaginary numbers, or thinking that we could square root negatives, right, or that there exist numbers that square to get a negative, they were really shunned, and people just thought they were just stupid, and these ideas they're coming up with were worthless. And it turns out that this branch of mathematics is one of the most widely applicable right now in our modern world to so many things that you use every single day, actually. And so the fact that if we remember that everyone's ideas are important, we can actually lift up people and hopefully bring out these ideas that maybe we don't understand, or we think they're weird, or they don't make sense to us, but maybe in the future they'll be very powerful, and it will help just bring everybody together, you know? Okay, so our learning goals for today. One main learning goal is to determine the magnitude, which is also the absolute value, or the distance of a complex number, as well as the argument, which is also the direction angle. We talked about prior knowledge imaginary unit, and then just remembering what a complex number is. Usually we use the variable z to represent a single complex number, and it usually looks like x plus yi. So you have like two coordinates. You can still think of them like coordinates, but we're just putting it in a slightly different way. A lot of times you would have seen this as a plus bi, that's fine as well. And just to remind you guys, we have a coordinate plane, and the x-axis, we can also consider the real number axis if this is to be changed into the complex plane. And then the y-axis is what we call the imaginary axis, okay? So the number 2 plus 3i, we can realize its position in two-dimensional space is you go over 2 on the real number line, and 3 is the imaginary portion, so you go up 3, so that location is right there. And that brings us just right into a little bit of review here of complex numbers. A single complex number is two-dimensional. So one single complex number is actually a two-dimensional object that's we just condense it into one thing. So you think of that one point in the complex plane, but it has two pieces to it. And it's just the same idea as coordinates, because it is a rectangular over and up or whatever kind of thing. It has two pieces, right? The two dimensions are the real part and the imaginary part, as we mentioned. And some vocab to remind you, this should be something that you've studied in the past, but if it's not, it's okay. The magnitude or absolute value, remember that means the distance from 0? But since we're in two dimensions, the distance from 0 would be the origin, and since it's in two-dimensional space, how do we find the distance in that way? Well, it's really just the Pythagorean theorem, right? So that's why it's the square root of x squared plus y squared. If you look at this example here, every complex number has a distance from the origin, and we usually represent it by a little arrow, and it's called a vector, okay? And this vector right here represents that the length of the vector represents the distance, and then the angle that's at, we can still call it theta, represents its argument or its direction angle, right? And you remember that this has a right triangle associated with it. So this would be like my x and my y. So if x squared plus y squared equals the absolute value squared, or the magnitude squared, then the magnitude is going to be equal to the square root of x squared plus y squared. And then we've just recently been reminding ourselves with trigonometry, we remember if I want to find the angle itself, right? Well, if I know the y and the x, which I do know those things, right? You remember that cosine and sine both require to know the hypotenuse or the radius of the circle, but since right now a complex number has the x and the y coordinate given, basically, tangent is the relationship that involves those two things, right? Now, I mentioned here that it only works in quadrant 1. Why? Because if you were to look at a complex number over here in quadrant 2, let's say there's a complex number right there. If you were to plug into your calculator would give you an angle that is, and remember, we want this angle here, right? Your calculator would give you possibly this angle or something like that, right? And so, or it might give you a negative or whatever. And that's just because what we studied recently about the inverse functions and their domains and ranges having to be restricted and stuff. So you have to do a little bit of thinking to figure out what the argument is, right? What that direction angle is if you're in a different quadrant. But luckily we know we can relate it to 180 or 270 or 360 to figure out that, okay? So, with this in mind, a little bit of review we've done here, let's just dive into a few examples. It's not going to be a very long one today. Alright, so this is one I just want to start out by giving you to do yourself since we remembered, the formulas and how to find things. I forgot to mention though, this capital C with like a bar in it, that just stands for a complex number. Just like the capital R with the bar stands for a real number. I'm just reminding you of those symbols because I'll use those for a shorthand sometimes. So this says for the complex number z equals 4 plus 10i, plot z, find his magnitude, and find his argument. So go ahead and pause and do that now, and then we'll look together at the solution. All right, let's go ahead and check. We're going to plot z. Remember that was 4 plus 10i, so we go right 4 and up 10. And I also graphed the vector, so I drew that in directly from the origin to the point. And I also mentioned that the specific angle we're looking for here is theta. And remember, the angle is still from the positive x-axis, like we've been doing with trigonometry, and around, right? So this one's straightforward because it's in quadrant 1. So you can go ahead and just check your calculations. The most simplified, well, square root 116 is the exact. If you wanted, you could write it as 2 root 29. But if you want to get a better handle on that actual length, it's about 10.77. And then again, just using the tangent inverse here, you get about 68.2 degrees, and that looks pretty accurate to this, right? We'll do another example where it's in a different quadrant soon, but you can check that for yourself. Let's go ahead and dive into another. All right, this is just another similar one for you to do, so go ahead and copy this down. In this case, we're calling this complex number v, and it is now 5 minus 12i, but we're going to repeat the same exact things that we did for the last one. So go ahead again and pause and do this on your own. All right, again, go ahead and check your work. We now have a complex number that is in quadrant 4. And just to remind you guys, the angle that's associated with this is this one right here. But your calculator, as you see here, if you apply the tangent inverse, is going to be spitting out this negative angle for you. So this is the location. If you actually apply the absolute value, right, the magnitude, remember that's distance from 0. So what we're saying is the length of this vector is 13 exactly. And then the last thing here is the argument, which is that direction angle, right? So if we directly apply the tangent inverse, it gives you this, but you and I both remember that we need to have the positive angle from the x-axis going around this way. And so because this is a difference from 360, the easiest way to deal with this here would be then to say the argument is 360 minus this 67.38, and that's going to give me about 292.62 degrees. Okay, so just a reminder for you, take a look at what your calculator spits out when you apply the tangent inverse, and then you have to discern what angle that is, and then use what you know about the symmetry and stuff within the quadrants to figure out the angle we need based on how we measure angles. All right? Let's just ask a few more questions that deal with magnitude and direction and get us thinking a little deeper before we end. So we just looked at the complex number v, which was 5 minus 12i. And number 3 says, use the results from number 2 to find the magnitude and argument for each of the following. They're all related, so I'm going to ask that you don't do any new calculations at all, because I'm going to say you should be able to use only the results from number 2, and maybe plotting these and looking for symmetry and stuff like that to be able to answer the magnitude and direction. So pause right now and do that yourself, and then again we'll come together and we'll look at it. Okay, so let's take a look at these. So you'll notice that they're all related, the numbers, right? Except we've swapped around all the signs. And you'll notice they form a nice rectangle with each other. The one that I gave you originally was v, 5 minus 12i. Well, if you look at 5 plus 12i, remember that that's v bar, right? That's his conjugate, because the conjugate just switches the sign for the imaginary part, right? So we're going to give that a name of v bar. I'll just use this for reference. You didn't have to do this yourself. And interestingly, if I do the negative of v, so I apply a negative to all these, that becomes negative 5 plus 12i. So this one right here is the same as saying negative v, but he's up here. And then negative 5 minus 12i doesn't really have a special relationship, so I just decided to call it w. Okay? So this one's the opposite, this one's the conjugate, that one's just whatever it is, reflected across the y-axis. And let's take a look at your answers. Remember, we can use the result from last time. We realized this was negative 67.38 degrees, so that means this one is positive 67.38. I realize I made a mistake right now, so I'm not even going to stop my video, but I did a bad thing. No, actually I didn't. No, I didn't make a mistake. Never mind, we're good. And then this angle here can be found from subtracting 67.38 from 180, right? So for negative v, his direction here, I can just take 180 and subtract that angle. And so that gives me 112.62. Similarly for w, I can just add that angle for the argument, 247.38. And then this one, we already have that. The other thing to note, what about the magnitude? Well, hopefully you realize at this point, since they're all equally distant from the origin because we've just swapped the signs of the coordinates, they all have the same magnitude. So the magnitudes are all 13. So, good job on that one. Let's look at just a couple more things. Alright, the last thing for this lesson, a new vocab word that's important, and a theorem. The norm of a complex number, and this should be brand new to all of us, I think. And we'll call this z and x plus yi, so that's our complex number. So the norm will denote n of z. It's just like a function, okay? And, well, it is a function. It is the product of a complex number and its conjugate. Don't forget z bar means his conjugate. So x plus yi times x minus yi. And our theorem states that the magnitude of a complex number can also be found by taking the square root of the norm. Okay? And this is something we can easily realize that must be true. Now, you remember, now I put this in quadrant 4, but no matter where my complex number is, x squared plus y squared, even if one of these is negative, when you square it, that's gone, right? Is going to give me the length of this squared, right? So this guy is the square root of x squared plus y squared. Well, let's go ahead and realize that the norm is x squared plus y squared. Remember how we multiply these out? So we're going to distribute everything here, and we're going to get x squared plus 2y, plus yi minus yi, and then that's going to give me minus yi squared. But if you remember, I squared is negative 1. So if that's a negative, and I squared is negative 1, these cancel out, and it just gives me x squared plus y squared. So, important thing to remember here is the product of a complex number and its conjugate is always going to be x squared plus y squared, no matter what. And so, the square root, and remember this is the norm, so the square root of the norm, aka the square root of a complex number and its conjugate, is a formula we can always use to figure out the magnitude of a complex number. So we'll be using the norm for things later on. It's going to be very helpful. And that's it for our lesson. So happy math, and you guys have a wonderful day. We'll see you next time.